Okay, so how does this family-based approach work? So the general idea is that we want to be able to apply to software product lines any IFDS-based analysis that were previously developed for regular programs. That's also why the approach is called SPL lift. So we sort of want to lift existing IFDS-based analysis that anybody wrote, let's say for a regular Java program without variability, so that this same analysis can transparently be applied to product lines without any changes in the code. So the analysis developer ideally should require no knowledge about product lines whatsoever. We really want this problem to just simply go away. Something that we will exploit here is that IFDS problems are actually special IDE problems, right? So if you remember my lecture about IFDS, then you will remember that IFDS problems can be cast as IDE problems with a very simple domain, with a binary domain, right? So basically, you can have a binary domain that only has top and bottom, or you can also say true and false. And for instance, you have then an edge function, or in the end then also jump functions that compute true if a certain node in the exploded supergraph is reachable in the IFDS problem, and otherwise it computes false, right? So that way you can really encode IFDS in IDE. And we will now basically assume that you have such a representation, right? That you have implemented IFDS in such a way by using basically an IDE solver with such a binary domain. But then we replace this domain using a richer constraint domain that takes care of the different feature configurations. So it basically tracks the different Boolean constraints that represent these configurations to keep track of the variability. And on the next few slides, using concrete examples, I will show to you how this works. So if you only remember a single slide in this lecture, it should please be this one. So let's assume we are given a program with a certain statement, and our existing IFDS-based analysis computes this flow function for this particular program statement, right? So it's not important what statement it is. It's not important what program analysis even it is. We only assume there is a given statement and there is a given IFDS-based analysis, which for this statement generates this partial exploded supergraph here, okay? So it forwards, for instance, some tanh from A to B. Yeah, that's what this could represent. But the statement is guarded using such an if-def-f, right? So the statement only is present in the code if the feature f has been enabled. Now, what does this mean? This means that this data flow here, it's only present in the program when the feature is enabled, right? So if it's disabled, this data flow cannot happen because the statement isn't even there, right? So in order to express this in the static analysis representation itself, we are now doing the following, and that's really the lifting. We are now annotating exactly these data flows that we previously saw with this feature constraint f, right? So we are basically putting a constraint on here, which tells us that these edges only exist when f is enabled. Now, obviously, the other question is, but what then happens if f is disabled, right? So think about this. If f is disabled, the current statement isn't even in the code, right? So basically, we can say it has no effect. And how do we represent something that has no effect? Well, using the identity function, right? So we basically will have a copy of the scenario here, right? Where we have the identity function, okay? But this time all the data flows are labeled with not F, telling us that these data flows are only valid when F is disabled. And now we can have both situations, right? So either F can be enabled or disabled, and upfront we don't really know, right? So we want to analyze the product line under the assumption that both could be possible, right? We don't want to constrain that upfront. And that's why we are basically doing a disjunction over both of these cases. So we're basically doing a disjunction over this graph and this graph, which in terms of graph reachability means that we have to do a graph union. And if you do a graph union over these two graphs, you end up with this graph. So basically it has all the edges from this graph here and all the edges from this graph here in union, right? The only special treatment that we do is that if we have an edge such as here and here, where basically both constraints like F or not F, right? When you take their disjunction, that this disjunction equals to true. So it basically means the edge occurs in every single configuration, which is certainly the case for edges that bring us from the tautological zero effect to itself, right? This edge is always there. Then this we can simplify, right? So if we have an edge that is labeled with true, then we basically have an unconditional edge. And that's why I'm also drawing it this way here. But all the other edges, they remain conditionalized with these feature constraints that we see here. Now this is the very simple case for a normal flow function, which you can also see here, right? So in the general case for a normal flow function and non-branching statement, you have this enabled case and you have this disabled case, and then you take the disjunction and you get this lifted flow function. You can also use this same principle that I'm showing on this slide for call to return functions at invoke statements, because essentially they have the same kind of data flows. They also propagate intra-procedural data flows, just like normal flow functions. But there are also other situations. So for instance, you can have a normal flow at an unconditionally branching statement. So for instance, that can be a go-to statement or a throw statement. So that is a statement where the control flow does not continue at the next statement, but at some other statement, right? And now also such a statement can be enabled or disabled, right? And the interesting case is when it's disabled, because if you disable a go-to or if you disable a throw statement, then that basically means that you don't jump, right? You do continue at the next statement in the program order. And this means in the enabled case, if this is your branch target, so the target that you go to or throw to, then basically your data flows have to be connected here, right? So if this statement is again guarded by F, then your data flows have to reach here. But in the disabled case, your data flows have to instead be connected to the next statement in the program order, which I'm denoting by these nodes here, okay? So this is denoting that you don't jump. And your data flow solver basically has to take care of this. And again, we can compute a lifted flow function. That's always the same principle by simply doing a disjunction or a graph union over both of these graphs, and that gives us the lifted flow function here. What's interesting here is that in this particular case, even edges that relate to the zero node can become conditionalized. Why is that? Well, normally I told you that the zero effect, it's always true, right? So it's the tautological fact. But in this case here, you can have configurations in which certain lines of code are not even reachable, right? So if in a certain configuration you always go to this statement here, then maybe that code is unreachable altogether. Or in the other case, if this is always disabled, then maybe you never jump to this code in the first place, right? And so basically this condition on the zero edge here, it tells you under which circumstances, in which configurations, this statement that this zero node relates to is actually reachable at all. The same here. Now you can also have conditional branching statements, like in Jimple, you can have an if something go to statement, right? That would be a conditional branch. And in this case, because we are not evaluating this runtime conditional, we are basically connecting these edges to both targets, right? So we are saying that the control flow could go to the branch target, but it could also go to the next statement in the program order. And the same is true also for the affect that we are tainting here. And again, the disabled case is rather simple, because if the statement is disabled, we definitely do not jump, right? Then we definitely move to the next statement in the program order, which is reflected by this. And again, you can lift this. Then you can have call flow functions and return flow functions. So now assume that this is actually the entry point for the call target, so for the callee procedure. Then the call flow function will map there if the call is enabled. If a call is disabled, we don't do anything, right? Because if a call is disabled, if you are sort of commenting out a call statement, or not including it in the code because there's an if-def around it that has been disabled, then the call simply does not happen. But there's also no side effect else on the current procedure, right? On the caller procedure. Any side effects on the caller procedure are taken care of by the call to return flow function. But here we are only talking about the call flow function. So that basically can be entirely disregarded. And therefore here the lifted flow function, it only looks like this. And the very same conversely is true for the return flow function as well. Because obviously, if you have a return from a procedure call and that procedure call never happens, then also the return should not have any effect. Now this is how that should work. Now as a little exercise, I'm asking you to draw the lifted exploded supergraph for this example. So here we are assuming that we have an IFDS-based taint analysis, like I showed you earlier, for that particular example. But now we want to lift it using the approach I just showed you. So draw an exploded supergraph that has feature annotations on the edges. And this will certainly take you a few minutes, so I encourage you to just pause the video now, do this in your own time, and when you're done, you can simply return to the video and I will explain the solution to you. Okay, let's look at the solution. So what I've drawn here is exactly such a lifted exploded supergraph. Here I did it under the assumption that we are not using the IFDS on-the-fly algorithm. You remember there's an on-the-fly algorithm, for instance, that avoids the computation of such data flows here. Y was never tainted in the first place, so we would not actually track this. Here I did it without this optimization because that makes things a little bit simpler. So here we have the same feature annotations we had before, right? So this statement here is guarded by a feature F, this is guarded by G, and this statement is guarded by H. Here we still have a feature that is not guarded, this is also not guarded, so this part up here, it's pure IFDS, right? So here we are tainting X, and X remains tainted here. But now here we have a conditional data flow, right? Because let's take a look at this. So this is telling us that X is overwritten, so it's being killed under the assumption that F is enabled. Okay, so that means the data flow from X to X is only retained if X is disabled, right? So that's why this edge is actually flagged with not F. Okay, so this basically comes out of the disabled case, out of the identity function, basically, right? Y is never touched, so here we remain at the identity function in all cases. Now we have a procedure call, okay? But this call is guarded by a feature G. So like I showed you, this call edge is actually also annotated with G. And the same for this call edge here. Here we have a statement that again overrides P, but only in the case that H is enabled. So again, similar to what we had here, also here we have annotated this edge with not H. And then again, the return edges here, they are also guarded with this feature constraint G. Okay. Now, these are the constraints that you have basically as edge functions on the individual edges that we draw. Now, what IDE will now do by the way we construct this is that as it follows such a path here, constructing intermediate jump functions and then in the end summary functions for the procedure, it will actually combine these individual edge constraints using conjunction, because after all, if you want to follow such a path, it means that this constraint needs to be true, and also this constraint needs to be true, and also this constraint needs to be true, and so on, right? And if you do this, you will get these intermediate constraints, right? So at this program point, we will have not F from here and G from there, right? So that's our intermediate constraint here. We have this intermediate constraint down here, which then also reaches this program point, and that's our final constraint here. So basically, that means that at composition, when we have such a feature constraint on this edge and this one on this edge, when we compute the jump function that brings us all the way down here, we are using conjunction, right? So in essence, that also means when I write the letter F here as an edge function, it really is a lambda function telling us I have some incoming constraint C that I've already computed up to this node here. And now I'm computing C and F, right? So I'm taking the conjunction of the incoming constraint and this feature F here. And then the same here, right? So I have an incoming constraint and I take the conjunction with G, and that brings me the new constraint down there. But then I also have a join or a merge point, right? And here we will do the inverse, right? Because if we have such a merge point and we are applying a join or meet operation, then it basically means, well, we could have come to this point using any of these two paths, right? So here we could have come to this point, to this fact, actually, at this program point, if either F is enabled or G is enabled, right? And what's important here is in order to do this efficiently, we really now need IDE, right? So we can't get away with IFDS because here, this is really a non-union merge operator, right? So we could also store this by using a set-based representation, by doing a set union, right? So F, comma G. But that would be less efficient, right? Because here we actually have a constraint-based representation, so that's actually a Boolean constraint. And that means if we have a number of these, we can actually do Boolean simplification on these constraints, right? So for instance, if we have F or G and not G or something like that, we can actually simplify these constraints, which you cannot really easily do on such a set-based representation. In particular, if you wanted to do this, you could not do it in IFDS, because in order to do this, you would have to be able to actually provide the simplification operation in the first place. And IFDS doesn't really provide any such feature, right? So IFDS, it only always does set union here and nothing else. Yeah, but in the end, this is basically what we compute, right? So you end up getting this constraint here over this path. And if you now look at this particular node that we are interested in here, right? So we want to know whether y can be printed in any certain configuration. Then we basically have this constraint here. And that is actually, if you look at the full constraint, this is actually true, which is our starting constraint here, because at the beginning, 0 is always true, it always holds, but at the beginning we assume that no other fact holds, right? So all the other ones are false. So we have true and this constraint that comes from here. And actually also the return constraint G here, okay? Sorry, this one, G here, right? Or we have false, which comes from this branch here, right? So we have false and not G, which gives us false along this branch here. And we do a disjunction because we can come along this branch and we can come along this branch. And now the point is that we can simplify this, right? So we can simplify this constraint, and that gives us not F and G and not H. And that's exactly the right constraint now, right? So if you look at this again, that's exactly the same configuration that we also saw earlier, which has the data leak, right? So if G is enabled, so we have the function call here, but F and H are disabled exactly then, and only then do we have a data leak for this product line. And that's the beauty of it, right? So now we conducted a single analysis using a single exploded supergraph for the entire product line. Granted, it's a small one, but it is a realistic product line. And in one single shot, using only IDE, not even, general monotone framework, just using IDE, we were actually able to determine exactly the configuration space under which these data leaks can happen here. And we also exploited no particular property of the analysis, right? So now I explained to you this is a taint analysis that we have here, but it could have been any IFDS-based analysis, right? It doesn't really matter to us. We made no assumptions about the analysis. We made no assumptions about the program. You could have used any IFDS-based analysis and it can always be lifted this way. And yeah, that's basically the general idea behind the approach. There are some interesting technical details, though, that I still want to discuss with you. In particular, it is a real challenge to find efficient representations of these Boolean constraints that we compute here. These constraints can get large, and therefore they need to be handled. And in the next video, I want to explain to you how we went about this and also what still the open problems are or challenges in the space right now.